Welcome to Red Hat Summit, and thank you all for coming. My name's John Shakshober, or Douglas John Shakshober, which is my official name. My nickname's Shak, and what we're going to do is, rather than just hear my boring voice and Larry Woodman, who have been doing a lot of this performance talk for many years, is we're going to, we brought in some of the other key both developers and performance optimization guys on my team with Larry, and essentially break it up into some parts. So we're going to be doing part 2, and we will give you a small time to break if you only want to go to part 1. Again, Larry Woodman is a senior consulting engineer at Red Hat and covers our a lead architect in our virtual memory for Linux. He's accompanied by Bill Gray on our team. He's been doing a lot of NUMA research, non-uniform memory, and wants to share some new things we're tech preview, but also new things in Red Hat 6. And we're going to allude to some of the work going on upstream in some of these cases for future releases of Red Hat Enterprise Linux. And then second part is Jeremy and I. Jeremy Eder is one of our lead performance engineers on the network side, and he's going to give you a good set of tuning and optimization for networks that's being done and available in Red Hat today, and again allude to things that may be going on upstream in the future. And then I'm going to wrap it off with some essentially we do have some slides on tools and some slides on how do you use these things to debug and optimize? But quite frankly, even though we have 2 sessions, we rarely are able to get through all our slides. So I apologize up front, although it seems like you've come here to learn this stuff. So we do share not just the tuning, but also kind of case studies on how much performance this is buying us in the lab and on test systems. So. Yeah, so I'll just, when you guys hop up, you can introduce yourself again. And I'm just going to start off with, essentially, Red Hat 6 now is extending the CPU counts in a single box up to 4K. And so we've been doing scalability on Red Hat 4, 5, and 6. I've been in 8 years of doing this. And Larry, are you 10 now?
9.
9, almost 10 years.
Oh, wait, at Red Hat, 11.
11
yeah.
years. So, but I did want to share, this is also a theme of cloud, right? So we really are the foundations of cloud in terms of both the kernel and the base OS. And then other talks in the show are about both virtualization, Rev, KVM, as well as Red Hat OpenStack. Everything is sort of fundamental, based on getting Red Hat Enterprise Linux tuned and optimized, because even though clouds, you may want to just kill your guests and you can add more nodes, you don't want to have to buy twice the number of nodes for your cloud to get to a certain capacity. And so briefly, one of the industry ways to understand performance is a whole set of industry standard benchmarks, and my team brings those benchmarks in. We're part of the consortia, and we do run benchmarks, but more importantly, we don't necessarily publish benchmarks. So we actually help our partners, and many of you are out there that have worked on industry standard benchmarks, optimized, and essentially vendors are allowed to choose whatever OS, applications, whatever gives them the highest performance. And so, not going to go through in full detail. You can see the mix of results out there, right? And so I don't want to make this a marketing presentation because you guys would throw half-rotten fruit at me. But what we are seeing instead, I'm just going to count the number of benchmarks our partners are doing and publishing on Red Hat Enterprise 6, for instance. And you can see whether it's a CPU load, virtualization load, JBoss, or middleware result, and Java results. More and more people are choosing to benchmark with Red Hat Enterprise Linux, OEMs, and so we're seeing a pretty strong growth. I mean, don't necessarily want a monopoly, right? but it fundamentally shows that the kernel and its capabilities turn out to give them the highest performance on x86 hardware. And remember, you can pick OSs, you can pick applications, etc. A similar thing happens and so the spec stands for System Performance Evaluation, and there's a whole suite of workloads. Transaction Processing Council is is pretty much database performance. And again, similar trend, much harder benchmark, must be audited. There's less results, so I'm just giving you the percentage of partners that are choosing to use Red Hat. And so what I'm going to do is, that's a prelude to the guys that are going to share why the low-level kernel scaling capabilities. Here's a quick example. We have a third party that did a bunch of studies. And so in different sections, you're going to see, this is a CPU load LinPack, and its scalability versus Windows, and so we're not the experts at tuning Windows, so a third party was chosen to do that. And more, if you look at the high end here, there's about a 20% difference today in this particular market segment. As we go through file systems, network, and Java loads, we're going to show you some of those differences as we go, but the point isn't necessarily the top performance. It's actually how we're going to deliver the performance with some of the tools that we have. And one of the biggest tools in RHEL 6 that was new is an infrastructure called TuneD. And TuneD is going to set various Linux tunables, and it's going to cater those tunables to your real customer environment. And so you're going to see things like the default, we believe, is quite a good default for Linux, but it is the same default that gets used upstream when we did RHEL 6. And so you'll see things like enterprise storage, low latency, throughput performance, and even a couple virtualization profiles for you to easily set and try them out. And if it didn't get performance, you can return your servers to their default configs. If you like them, they'll be persistent across reboots. So it's a nice infrastructure. Some people use the same infrastructure to change their own tunables and customize it for their environments. And so that being said, I'll jump over to Larry Woodman, who is going to discuss scalability and huge pages.
All right, so first thing I'm going to do is say that what I'm going to go over is some of the parameters that the TuneD profiles actually change, and talk about what they do and why we need to change them, and maybe discuss enough about them so that if you need to make finer adjustments, you can do this. So one of the attributes of RHEL 6 is the new schedule, the completely fair scheduler. It supports, there's several tunables that allow you to control its quantum and so forth, to return it to similar values that they were in RHEL 5 if you had better performance gains in RHEL 5 and so forth. So the first thing I want to talk about is the fine-grained scheduler tuning. These parameters, the sched-min granularity and wake-up granularity, nanosecond parameters, control the quantum size and how frequently the system context switches and potentially runs out of a quantum. The lower these values are, the more rapidly it will respond to devices, external events, so the latency will be better, but going through the scheduler more frequently can be a trade-off in throughput. So two of the parameters that you'll see adjusted in TuneD are these, and basically they're increased in several of the TuneD parameters in order to give the system quantum, create the system quantum larger. So, another one is load balancing. When a CPU goes idle, rather than just letting that CPU do nothing, what it does is it looks around at all the other CPUs on the system and sees if their load average is greater than 1. If they got extra work, then what they'll do is they'll try to migrate that work over to their CPU, so you don't end up with like multiple idle CPUs on the system and multiple CPUs with queues of work to do that are greater than 1. However, this is a trade-off. The more frequently you do this, the more you migrate tasks around and overload the scheduler. But on the other hand, if you don't do it frequently enough, you end up with situations in which CPUs are idle and other ones have load averages greater than 1. So this, we've found that there are several benchmarks in real-world applications that run better by increasing this by a factor of between 2 and 10. This is the benchmark result. You want to talk about this?
Yeah, so again, we jumped right into it, but one of the things I think Larry and I like to try to figure out is how many people are running Red Hat 2.1? Because the exit sign is, no, no, seriously, how about Red Hat 5? Okay, cool. And RHEL 6, we're hoping a lot of hands there.
Yeah.
And how about 4? I'm sure there's, okay. So again, what partly we do is kind of contrast usually 5 to 6, but most of the things that we say between 5 and 6 also can kind of extend back to RHEL 4 as well. So this example is using that sched migration cost and tuning that to a larger value will actually prevent it from scheduling more frequently. And so we showed you an effect on a benchmark that is literally just looping on system calls, both exits and forks, and you can see some reasonably, greater than 20% performance gains. The other piece that this really helps is keeping high, so if you're running lots of virtual guests or you're running multi-tenancy databases and things like that, we find bumping this value up can actually it's not just pure performance, it's about fairness. It's about allowing coarse-grained scheduling here to have more time, before things get scheduled around. And so a slide I didn't put in here, because it may be in some of the virtualization decks, is we had an example of 16 guests running 8 to 16 guests simultaneously doing I/O used to vary 30, 40% and get, say, value X. Setting this value much higher helped essentially maybe only gain about 5% in any given guest, but the fairness at which the guest response times were much more level across that. Okay. And Bill or Jeremy, any other examples?
Well, I would say that if you're doing manual affinity pinning, how does this come into play?
Yeah, and so again, if you are pinning the systems down to certain cores, et cetera, in benchmark environments, you probably don't need to adjust this because it's sort of setting those schedule, it's not allowing you to do cross-scheduling. So is that right?
Yep.
Okay.
All right. So another parameter we'll see is what we call child runs first. It's the reason I put this in here is the default behavior is different in RHEL 5. By default, the parent continues to run before the child is the default. And there are cases in which on systems that have load averages greater than 1, the system has got very busy run queues that it's necessary to change this back to the way that was in RHEL 5 for performance. The next thing I want to talk about is huge pages. The Intel architecture supports 3 page sizes, 4K, 2 meg, and 1 gigabyte. And there are multiple ways of controlling how, what page size different regions of a process's address space uses. Our conventional huge page mechanism is manually controlled through procsys VM under nr_huge pages, and it's also controlled through the sys file system for finer control. And for gigabyte huge pages, oh, by the way, the conventional huge pages, you allocate them when you echo a value into this file, and you free them by echoing a 0 back into you just delete them all, and the pages go on and off these queues and back onto the free list and gets managed by the kernel itself. Gigabyte huge pages are a boot time optimization only. Currently, there's a boot argument, or 3 boot arguments that you specify. I want a certain number of gigabyte huge pages. And what this does is rather than having the kernel manage these tiny little pages, it manages a gigabyte of memory at a time. Each TLB entry maps a gigabyte rather than 4 kilobytes at a time. And then finally, the last thing I want to talk about is transparent huge pages. These are 2 megabyte pages that are used in anonymous regions of memory, and the kernel does this all for you automatically unless you shut it off. And there are a couple times in which the system performs better with it shut off, and I'll go over those. As far as standard 2 meg huge pages are concerned, this is just an example of how you allocate them. You allocate, when you allocate, say, 2,000 huge pages, doing it through the proc file system will evenly allocate them round robin on all the nodes. And then, as you can see, it'll show you how many are free, and then when they're used by running a program that uses them, you'll see the free go down and the reserved, the free go down and the reserve go up, and as the process touches these pages, they'll actually be used. As far as 1 gigabyte huge pages are concerned, these are the boot arguments. You pass in the huge page sizes as a gig. And you want, in this example, I had a 16 gig system and I said I want to show 8 of them in use. I want to use 8 of them. And once again, you have to reboot the system in order to do this. And running an application that uses them, you can see that the total number of them, it's just the number free just goes down to 0 as they're used, and there's no other control that you have over them, over a boot. Once the application exits and the pages are freed, they're using System 5 shared memory. Once they're freed, they just simply go back onto the free list for the next application to use them, but they never go back to the kernel's managed page pool. If you allocate them and then don't use them, you basically run your system with less RAM. And then finally, transparent huge pages. Here's just an application that I wrote that consumes, say, 15 gig of memory. And by using transparent huge pages, you can see we got a speed up of about almost 2 times, about 50% speed improvement. And how you see that you're actually using these is with the non-huge pages in in proc meminfo.
Yeah, so before we move on, so huge pages traditionally came from database caches, right? Shared memory segments.
Yep.
that use them, or Java engines. So anybody using huge pages today? Okay, and the subtle point I think Larry was sharing is that the other thing that the huge pages are, it's we echo it in dynamically. Obviously, you can set it in a sysctl. So that per reboot it'll be there, and that memory is wired down, right?
Right.
And
the kernel doesn't touch them, so it doesn't get in the way of the use of them.
Right.
It hands them over to the database for use.
And so it's a very common way. Database talk is given next by Sanjay Rao of getting really nice performance gains in databases. We're sharing. I think you're looking at the slide now of Java engines, some of the performance gains you can get. And remember, each of these workloads that we're running, it's not like, oh, we gained 9% because we had 20%, we had 10% idle, right? No, that we had saturated the resources on the system in the past, and the huge pages are essentially using the hardware more efficiently, right? They're not taking TLB misses, or much less TLB misses, and then each system, whether x86, you know, we're not the chip designers, but they have a different footprint of how many, you know, the different number of TLBs, and so your mileage varies on how much performance gain you will get from this. But more and more, as you start accessing, you know, 100 gig of memory with an application, or you start running 50 guests on a system with half a terabyte of memory, using a huge page, and we'll get into it in a little bit, but KVM can actually use the transparent huge pages dynamically. In fact, it does when you start it up for cloud benchmarks. Or you can still manually set up these static huge pages and get the difference in performance if you want to manually control your
Right.
environment. So, and I think, what do we get for a 1 gig page? We got another 2%, 3%.
Yep.
So it's really a function of how wild, you know, your memory access patterns and how much you're missing the translation buffer. And if you're interested, there's other talks using the perf tool. You can actually measure that today with the perf tool. So.
Mm-hmm. And the next thing we're going to talk about is NUMA. And before Bill sort of gets a handoff, I just wanted to talk about a little bit about the internals of the kernel and how it deals with and manages it. Basically, memory. We'll start off with memory. Memory is in zones. So this is just a picture that the first, say, 4 gigabytes of memory on a 64-bit system. I don't talk much about 32 anymore, but the first 16 megabytes and 4 gigabytes of memory are called the DMA zones. This memory is sort of held onto for the very last minute in case some device needs memory that must live in the first either 16 megs or 2 gigabytes. And the rest of the memory is called the normal zone. And the system manages these memories, this memory through page lists. And we have what we call a split LRU page list. We have a list of anonymous pages and list of page cache pages, and the system manages these pages, sort of these lists, independent of each other and in cooperation with each other. So I'll just sort of get to a picture here. So on a per NUMA node basis, we have these page lists, and each NUMA node has anonymous and file LRU pages, and we have active and inactive lists, and the pages migrate as they age. They migrate from active to inactive and then eventually get freed. And what I wanted to say here is this is done on a per NUMA node basis. So it's actually possible to have, it would be possible to have a NUMA system that is actually out of memory on one node but is memory rich on another node. And then I think I'll let you go into the NUMA stuff. We'll go back and forth on this.
Yeah, so I'm Bill. I'm going to talk about some NUMA-related features, especially some stuff that's new in RHEL 6.4. How many of you are familiar with NUMA and how to manage it? A lot of you? Okay. Well, so as many of you probably know, NUMA is a solution to having too many CPUs sharing a single memory bus. And so these days, well, I should say NUMA's been around for decades, but really only the last half decade or so on x86 systems. But these days, memory and memory controllers are distributed on sockets, okay? And pretty much any multi-socket server system these days is going to be a NUMA system. And usually, there's one NUMA node, and I'll get into what that's about, per socket. On recent AMD architectures, there's actually 2 NUMA nodes because there's more than one memory controller on a socket. And so we're going to discuss various features for managing NUMA. First of all, it's very important that you keep interleaved access off in the BIOS. Otherwise, you will effectively have only one NUMA node, and as Larry already mentioned, there are various features that are in the kernel that work on a per node basis. And so if you turn off NUMA access by doing interleaved access in the BIOS, you won't get those multiple streams of activity going on in the kernel, and that's usually a bad thing. Okay, so here's a simplified drawing of a CPU, right? There's some number of cores sharing usually a L3 cache and some amount of memory and memory controllers. Now, actually, core count's getting very high these days, 10 or more CPUs on a socket. And of course, if you have hyperthreads, that doubles your logical number of CPUs. So there's a lot of logical CPUs in a NUMA node these days, and it's going to be increasing. Okay, so you can arrange these little NUMA building blocks in many different ways. Here's a simple 2-node system. There's a link between the sockets, and your NUMA memory performance is determined by the distance between your executing thread and the memory that it's accessing. So you could have a thread on node 1, core 3, accessing memory that's in node 0. And so clearly it has to go across this link to get the data that's on the other CPU. And there's many different ways to arrange these things. Here's a picture, a simplified drawing of a fully connected 4-node NUMA system. Some 4-node NUMA systems are actually, the topology is a ring, okay? And so clearly to get from node 0 to node 3, you actually have to go one way or the other through one of the other nodes. So there can be multiple hops, multiple levels in your NUMA topology. And furthermore, there might actually be important devices off of specific PCI buses that are only connected or have a faster path to one of the nodes and the other nodes. So it's important to know what your hardware topology is. You want to talk about
Yeah.
some of these, Larry?
Just to sort of follow up on a little bit earlier what I was talking about. So the kernel itself manages or maintains resources on a per node basis. It's memory, CPU, I/O DMA capacity, interrupt processing, page reclamation. So the kernel is actually running independently on, or has threads running independently on each one of these nodes, and they're sort of interacting between each other. So as far as what memory looks like, a typical NUMA system, the node 0 is where the lowest memory lives. So on node 0, it'll have 3 nodes, a DMA32 zone, and a normal zone. So if on, let's say, a 16 gig 2-node system, it would have 4 gigs down below that are in the DMA 2 zones, 4 gigs that are in the normal zone, and then the remaining 8 gigs want to be on a separate NUMA node, each one with individual CPUs. And although the CPUs can touch all the others' memory, there's a performance consequence of running on a CPU on one node and touching the memory on another node. This might be a little bit early to talk about this anyways, but there is also another tuning parameter that you will see altered, and it's called zone reclaim mode. This controls when the system runs out of memory, it controls whether the system should reclaim memory on the local node or simply fall off and start allocating memory on the next node. And the decision is made at boot time. It's right almost all of the time, but it looks at a table called the slit table, and it tries to estimate the performance consequences of going to another node. If it is a fairly tightly coupled NUMA system with with the direct links and so forth, it might actually be cheaper performance-wise to simply fall off into the other node rather than start to reclaim on the local node. And we'll talk about a little bit more about this later as we get into some of the stuff. So.
Yeah, so I'm going to talk about some of the tools to learn about your NUMA topology. And one of a very simple tool that gives you a lot of information is LSCPU. And you can see that it shows you how many NUMA nodes you have, how many sockets, and how many cores per socket and threads per core. Down at the bottom, note that it gives you the per node CPU enumeration. It's important to understand that when the system enumerates your CPUs, it's usually, the logical CPUs are usually not enumerated sequentially. So you see here they're round robin across the nodes, but there's different, depending on which manufacturer your system is made by, there's different ways to enumerate CPUs, and they're usually not sequential across all the logical CPUs. There's a nice GUI tool that shows you pictures of your topology called LSTopo. It's in the HWLock package. And it shows you a very, very nice visualization. This is just 2 NUMA nodes on a bigger system, but you can see the individual caches per core and the shared L3 cache and the memory like that. Okay, so Larry mentioned the slit data, and NUMA control, a -- hardware, is a very useful tool for actually getting to see what the internode latency cost is. Now you can see here that this shows the CPU enumeration again, and then the amount of free memory on a per node basis. But down on the bottom in red there is the system locality information table. And what that shows you is the relative access latency going from any one node to any other node. This is a 4-node system, so it's a 4x4 table. And you can see it's a fairly uniform, like fully connected topology probably. And on the diagonal, you see the 10s. The slit data is normalized so that 10 represents the cost of accessing normal local memory. And bigger numbers, like the 21, shows you that it's roughly 2.1 times as expensive to access memory from a neighboring node. And some of the remote latencies can actually become very large. So these are some typical remote memory latencies for a 4-node system or an 8-node system. Note the 32-node system especially. What this shows is that for any given node on that 32-node system, there's one other node that is relatively nearby latency cost-wise. Okay? And the other 30 nodes in that system are at least 4 times more expensive to access memory from. So it's important to understand which nodes you're using, and if you have some application or a guest that spans multiple nodes, in this machine you would really want to have them on those 2 low-cost nodes. Otherwise, the performance might fall off a cliff if it's using the remote memory that's 4 times as expensive to access. There's actually 2 things on this slide. The left half is dealing with bare metal, a native system, and the right half, those 2 columns on the right half, are virtualized. But what this slide shows you is that for both bare metal systems and virtualized environments, you can get roughly a 20 to 30% boost by doing proper NUMA tuning. And 20% is a typical, typical performance boost that you can get by doing NUMA alignment. And it's 20 to 30% represented here on, for both virtualized and bare metal environments. Okay. So Shaq and Lear already talked about the scheduler. It works really hard, and it thinks all the CPUs in your system should be working really hard too. So if it sees idle CPUs, it tries to spread out the work, the execution threads, to take advantage of idle CPUs. And it does a really good job of keeping the system responsive and using those CPUs. But the problem is that it moves your execution threads around sometimes without enough regard for where memory was initially allocated, right? And by default, memory is allocated on the node where the thread is currently executing when it does the allocation, right? But after that, the scheduler might move that thread around to a different CPU in that node or a different CPU on a remote node. And at that point, you're accessing remote memory. So Red Hat's working with the upstream kernel developers to try to make the kernel scheduler more NUMA aware, to implement automatic NUMA balancing. Hopefully that will be showing up soon in a version of RHEL. And I should also make the point on the bottom here that remote memory matters the most for long-running processes like a KVM guest or HPC application, or something like that. If your applications are short-running or they don't actually contend for memory much, it's not going to make that much of a performance difference. Okay. So Red Hat rewrote NumaStat for RHEL 6.4. It was a pre-existing tool on Linux systems, and it previously showed allocation statistics, whether memory was allocated on the node that it was intended to be allocated on. But it was rewritten to show per process, per node, per process, application memory, and we'll see some examples of that coming up. It's in RHEL 6.4. There's a decent man page for it. I encourage you to look at that. So by default, it's 100% compatible with the existing NumaStat. Shows whether NUMA hits are memory that was intended to be allocated on that node. NUMA misses is memory that was allocated on that node but wasn't intended for that node. And you see for any NUMA miss, you should have like a NUMA foreign up there, I think. And that's the node where the memory was supposed to be allocated but didn't go there. Anyway, by default, that's what you get from NumaStat, and that's what it used to be too. Any option in the new NumaStat will change the behavior. Here, it's showing just a compressed display. It changes the units to megabytes. And for big systems with many nodes, this shows you more information in less space. You can also, well, most of you are probably familiar with the information in procmem info. This shows the same kind of thing, but on a per node basis. And you can get that, I think it's the -M option. Okay, and so one of the very useful new features of NumaStat is to let you look at processes that are on the system. You give it a keyword QEMU, and the -C is to compress the display. And it will go look on your system for any process that has the QEMU pattern in it, right? Which, so in this case, it's the 4 KVM guests that are running on this system. And it shows you on a per node basis the memory distribution of that process. And you notice that for each of these guests, the memory is spread across multiple nodes. So that memory is not aligned on a per node basis for those guests. On the next slide, it shows the same guests with that memory aligned on a per node basis. Each guest is about 10 gigabytes. And on this system, it's possible to put all those 10 gigabytes on the same node for each guest, right? So before and after. Okay. And while we're talking about KVM, here's some suggestions. You should, if you have a choice, you should try to size your KVM guests efficiently. Don't give them many more vCPUs than the threads your applications running the guests will use, and don't allocate more memory to them than they're going to use. All right, the more efficiently or frugally you size your guests, the more guests you can get on the system, the more flexibility the system has to put them in a part of the system where they can run efficiently. And the last point here, if you have to have big guests that span NUMA nodes, you should really consider the system locality information data. Remember that 32 node system where 30 of the 32 nodes have a remote access latency of 4 times local memory. So it's important to put your guests in nodes that have a low internode latency. If you want to manage NUMA manually, there are many ways to do it. They all require some kind of planning, knowledge of the system topology, and you effectively have to allocate resources, decide how much of your system you're going to use for each application or each guest that you're running. And you want to bind both CPUs and memory, and depending on your workload, you might also need to consider devices and interrupts. And Jeremy is going to talk in the second half of this talk about some of those issues. But you want your CPUs, your execution threads, and your memory on the same NUMA nodes. And for jobs that you're just going to launch, you can use the NUMA control command and specify that you want your CPUs and memory to be on the same set of nodes. If you're using libvirt to start your guests, you can actually set things in the XML file, the NUMA tune tag, and tell it which nodes you want your guests to be allocated on. You can also use C groups with the CPU set controller to bind CPUs and memory to given NUMA nodes. A little more about C groups. Besides being able to bind your threads and your memory to the same nodes with the CPU set controller, you can also effectively set an amount of shares of resources that different processes will use. Do you want to say anything more about this later?
Yeah, I've got probably a half a dozen slides at the end of this.
Yeah,
I want to get into C groups a little bit.
If we have time, we'll come back to C groups and talk more about C groups.
And maybe we're just, so one, are you guys doing NUMA-like tuning already? Anyone? You expect the OS to do it automatically? How about C groups? Anyone using C groups? Or? Okay, similar set of people. So okay, yeah. So time permitting, we'll summarize this stuff after Bill's discussion on NUMA, and then if people need to come and go, maybe we'll step people through some of the C group discussion. But yeah, let's keep rolling. And it is a different way to, again, achieve NUMA capabilities, and in addition to the disk and network C groups that happen.
Yeah. All right. So yeah, maybe we'll come back to C groups in a few minutes. So I want to talk about NUMA-D for a while. NUMA-D is a new user-level daemon. It attempts to do NUMA tuning for you for big processes that are running on your systems. This was tech preview in RHEL 6.3. It's shipping in RHEL 6.4. And it improves NUMA performance significantly for some workloads. It's not enabled by default. Okay? There are some workloads that it's really not appropriate or that are not good targets for NUMA-D, and I'll talk about those in a couple of minutes. Again, this is in 6.4. It has a good man page. You might want to see the different options that are available. Basically, what it does is it repeatedly monitors the resources that are available on your NUMA nodes. So on a per NUMA node basis, it looks to see how many CPU cycles you have available and how much memory is free. And it also scans processes to see how much memory processes are using and how many CPU cycles are using. And it tries to match them up so that significant processes get put on NUMA nodes where there are available resources. And again, it's trying to do automatic NUMA tuning for you. that you could do manually with NUMA control and other things like that. It also tries to rebalance things if your workloads are variable and it's advantageous to move things around after initial placement. It'll try to do that. And that's one advantage that NUMA has over static placement. It responds to changing loads in your environment. Okay, here's a picture, before and after picture of NUMA. Conceptually, there's memory spread across all 4 nodes. After NUMA runs, they're aligned properly. We can compare that, if I can flip back here. Oh, too far. So there's a before picture, there's an after picture. NUMA moves the memory for each guest so that it's aligned in a NUMA node. And again, there's the conceptual picture of the same thing. This next slide, some of you might have seen this if you stopped by the performance booth. This is just a still shot from a little demo movie we had. And what this is showing you is 4 processes. Each process has 6 threads. And on the left side, there's lots of variability in threads. Each line represents a thread, and it's effectively the memory latency of the thread, how much time it's taking to access memory. And in the middle of that, in the tiny terminal up there, somebody typed NUMD, and you can see that NUMA moved these things around and aligned the threads with the memory. And towards the right half of each process graph, you can see the access time, the latency is almost uniform. There's a few little glitches, but the 6 threads are basically on top of each other. And note, more importantly, that line is not only uniform, but it's much lower than the variable latency in the left half part of the graph. And so that's a sort of a view of the memory latency effect to go along with that conceptual diagram here of what happens when you move the memory and you align it on NUMA nodes properly. Okay, so what NUMA tries to do is to localize and isolate your workloads in a fraction of your system, right? So it's intended for like a server consolidation environment where you have multiple applications on one server or multiple instances of an application, or maybe you decompose some bigger load so it'll fit in NUMA-sized chunks. That's the environment that it's really targeted at. And that's where it's most likely to have a positive effect. If you have a large system that's dedicated to a big in-memory database, that's not a good target for NUMA, okay? First of all, you can't take something that uses the whole system memory and localize and isolate that, right? Because it's already using most of the resources on the system. So that's not a good target. However, if you have multiple instances of a database running inside KVM guests, well, then it is a good target, right? Because KVM guests, if they are only use only a fraction of the resources, they might be able to be localized and isolated on the system. Okay, to start NUMA, you just type NUMA, and it starts running in the background, monitoring resources and scanning processes. And you can stop it from running by saying NUMA-I 0, and you're effectively setting the interval that it scans things to 0, and that'll terminate NUMA. Another option is to specify a utilization target. By default, NUMA tries to maintain some resource margin on your NUMA nodes. Okay? If you have carefully sized your workloads or guests to fit in a NUMA node, you might want to say something like NUMA D-U95 to say, it's okay to use almost all of the resources in this node, and don't worry about it because I sized it that way. But by default, it tries to maintain some margin so that the resources can absorb bursty applications. This is a picture showing, it shows the improvement you can get from manual tuning. The dark blue bars are the default performance from a Java load, and so the x-axis should be like 2, 4, 6, 8, 10 warehouses for this Java load. The blue bars are default performance. The gold bars are what you get if you do hand tuning with NUMA control before you launch the processes, and the red bars are the performance that you get automatically by running NUMA-D. And I knew how big these things were, so I actually ran NUMA-D-U95. But you can see automatically, without knowing anything about topology and without doing much manual tuning other than typing NUMA-D, I got most of the performance that you can get from doing expert NUMA tuning. So on this workload, it actually shows you can get a very large gain just by running NUMA-D. NUMA-D also has an option, it's called a pre-placement advice option, -W, and you tell it how many CPUs, for some impending or forthcoming load you're going to launch, how many CPUs and how many megabytes of memory you're going to use. And then it will look at the system and see where there's resources, and it'll give you a list of nodes where you should launch that application. Okay, so here's a shell script, too small to read, but what you need to know is that there's two halves that do almost the same thing. Okay, the first half asks NUMA-D for advice and promptly ignores it. Right, the second half asks NUMA-D for advice, and it uses that advice in a NUMA control command. And here I've magnified the important part, where NUMA-D is invoked with a -W option, how many threads I want, and how many megabytes of memory. And then I actually use the result from that NUMA-D query in NUMA control to launch this command called pig, which is just a memory exerciser, simulates pointer chasing workload. Okay, so here's the result of running the top half, ignoring the advice. And you can see the average score is approximately 40, 50. And this score, higher is better. It's kind of the inverse of memory latency. It's relative to that, so higher is better. Score's about 40, 50. Notice that some of the standard deviations for the 6 threads in each one of these processes are very large. I mean, if you have an average of 40 and a standard deviation of 13, there's some threads that are not really doing their share of work, okay? But now, if you use the advice that you get from NUMA-D launching these processes, all of a sudden you get more than double the work achieved, right? It went from 40-something up to over 100, and there's no standard deviation at all. So this corresponds to that picture of the graphs where the memory latency, the access time becomes very uniform and lower than when you don't do anything at all. And of course, you could do this without using NUMA-D, just by binding your jobs with NUMA control round robin. Okay, the advantage that NUMA-D gives you here is that it actually looks at your system to see which nodes have available resources at the given time. So it's better than just doing static, fixed binding. Here's another results slide. This shows a Java load inside of guests. And in this case, colors are the same for the bars. In this case, NUMA-D achieved parity with hand tuning for these KVM guests running Java loads. Here's an example of what we had is multiple instances of Oracle running inside of a guest. And hand tuning didn't get us a whole lot. I mean, it got us 10, 20%, or it's a little hard to see the bars there. But then when you oversaturate the system, the NUMA layout becomes even more important. That's the last column, the 80 user columns over there on the right. But in any way, in any of these 3 cases, you can see that NUMA-D automatically gets you close to what you got from manual hand tuning. Okay, so I mentioned that Red Hat's working upstream to try to get some of this NUMA balancing in the kernel. So what's going to happen with NUMA-D remains to be seen. Systems are getting bigger and more complicated all the time, so they will probably, both solutions will exist for the foreseeable future. NUMA-D has that pre-placement feature, which can automate placement of jobs that you're about to launch. So there's reasons for both of those solutions to continue. Some potential improvements for NUMA-D. Right now, it only does memory and execution threads. It doesn't try to get affinity for devices or interrupts yet. And sometimes you also have related processes that you would really like to run in the same NUMA node because they hand data back and forth. NUMA-D doesn't know anything about that yet, but that's a potential improvement too. Okay, so just to review a little bit what we talked about. We talked about TuneD, and the sort of the gang switch on all the profile settings so that you can set your system to achieve different kinds of performance depending on what your workloads are. Talked about transparent huge pages, both static and transparent huge pages and also static huge pages, and the advantages that some of those have. And we also talked about NUMA things, the new NUMA stack command, NUMA control for manual binding, NUMA D for auto placement. And we didn't talk about tuna yet. You got to come back for part 2, but that's a very nice tool which can be used for moving things around, isolating processes, and setting where interrupts are handled and stuff like that. But you got to come back for part 2 on that.
Right.
Okay. So
let's just pause here. Actually, I want to pause and let you guys, why don't we ask some questions if you guys haven't? And again, remember, so this is virtual memory of Linux. The reason we spent so much time on NUMA is about, I don't know, 60 or 70% of our performance problems or our optimization, you saw some of the gains we can get in these workloads. It comes by getting the NUMA memory and CPU placements and scheduler nailed down. And then the second thing that we're seeing is we're trying to go to more automated tools. So the scheduler in the future should be we hope will be NUMA aware, as we mentioned. And in the meantime, 6.4 has this automatic NUMA D daemon that yum install NUMA D and enable it and experiment with it. So and then finally the TuneD stuff we'll go into at the second part. We'll go into other workloads, how to map some of those workloads onto which profile.